If you find difficulties in solving the numericals of the thermodynamics, if you get confused between the formulas of the thermodynamics, how to tackle between them, okay, then this is the video for you. In this video, we will see the important key points of all the thermodynamics. The whole thermodynamics we will see in a glance, okay, so that you can understand whole the concept, okay. And if you are preparing for CSI, NET exam, GAT, IIT JAM, MSc, BSc level, any one, okay, if you are preparing for them, then you can see this video and you can get all the points of thermodynamics in your mind in one video. Okay, so let's start our video. Hi students, welcome in the chemistry classes by Priyanka Jain. So here we are seeing a crash course of the thermodynamics. We will see all the important key points of thermodynamics in a single video. So firstly we are starting from the thermodynamic variables. Actually there are three thermodynamic variables, that are pressure, temperature and volume. Okay, by varying them, we can vary the different thermodynamic properties. Now, there are the thermodynamic properties with which we deal in the thermodynamics. These thermodynamic properties are internal energy, that is denoted by U. Next one is enthalpy, that is denoted by H. Third one is Gibbs free energy, that is denoted by G. Next is entropy, that is denoted by S. And next is Gibbs-Helmholtz function, that is denoted by A. Okay, out of which this U, H, G and A, these are also known as the thermodynamic potentials. Alright. Now there are the non-thermodynamic properties also. It means these thermodynamic properties are not the state functions and these are not related to the state. These are work and heat. Next thing is the extensive and intensive properties. Extensive property means that depends upon the amount of the substance. It means it will change with the amount of the substance is changing. These are internal energy, enthalpy, Gibbs free energy, heat capacity, mass, volume, force and number of moles. The next one is the intensive properties. Actually, these properties does not depend upon the amount of the substance. It means these are not depending upon the amount. These are not changing with the amount of the substance. These properties are temperature, pressure, density, viscosity, refractive index, surface tension, specific heat, molar volume, molar heat capacity, boiling point, melting point. Actually, if you see any property with the term molar, prefix molar or per is per is present or specific is present, then these are all intensive property. For example, if you see molar internal energy, then it will be intensive property. Okay. Similarly, molar heat capacity is the intensive property. Now we comes to the next important thing, that is thermodynamic relations. Actually, there are different type of thermodynamic relations from which directly questions are asked in the exams. Okay. So first is the Maxwell relationship. These are the relations. Okay, I am showing you here the relations, you can just learn them, or if you want how to solve them, then you can see my lectures on the YouTube. The lectures are also available on YouTube. And if you want the detailed manner course, okay, if you want to see in the detailed manner all the things with the numericals also, then you can see my course that is available on our app. Okay, so on my app we have started the physical chemistry course in which you can see the thermodynamic course. Okay, so where you will see all the things in a very descriptive manner. So actually there is the tricks for this by which you can do. So for that you can visit our app. Okay, so here is the first relation, that is del T upon del V at constant S is equal to minus del P upon del S at constant V. Second relation is del S upon del V at constant T is equal to del P upon del T at constant V. Third relation is del T upon del P at constant S is equal to del V upon del S at constant P. And fourth relation is del S upon del P at constant T is equal to minus del V upon del T at constant pressure. So these are the Maxwell relationships. But actually there are also the non-Maxwell relationships. It means they are reciprocal. The reciprocal of the Maxwell relationships are also true. It means del V upon del T at constant S is equal to minus del S upon del P at constant V. Similarly, del V upon del S at constant T is equal to del T upon del P at constant V. Del S upon del T at constant S is equal to del S upon del V at constant T. Del P upon del S at constant T is equal to minus del T upon del V at constant pressure. Okay, So from here directly questions are asked, so learn all of them. Now see the equation of states. This is also quite important. First equation of state is del u upon del v at constant t is equal to t del p upon del t at constant v minus p. Okay. For ideal gas, actually del u upon del v at constant t, it means the change of the internal energy with volume at constant temperature is equal to 0. Okay, so this thing you should remember. One more thing, that del u upon del v at constant is also known as the internal pressure, and it is denoted by pi t. Okay, how to derive this equation you can see in our YouTube videos also, and also on our app you can visit. Now see the second equation of a state, that is del h upon del p at constant t is equal to minus t del v upon del t at constant p plus v. One thing you should remember, del h upon del p at constant t has units of volume. This question has directly been asked in the csirnet exam. The next thing is the thermodynamic coefficients. There are three thermodynamic coefficients, alpha, beta and gamma. First one is isobaric expansion coefficient. It means the change of the volume with temperature at constant pressure. Alpha, that is given by 1 upon V del V upon del T at constant pressure. For ideal gas, you can derive it directly. Put the value from PV is equal to nRT. You will find out the value alpha is equal to 1 upon T. Okay. The next thing is the isothermal compressibility coefficient. Beta is equal to minus 1 upon V del V upon del P at constant temperature. It means this denotes actually the change of the volume with respect to pressure at constant temperature. For ideal gas, it is equal to 1 upon P. The next one is the isochoric thermal pressure coefficient, gamma. It is denoted by 1 upon P del P upon del T at constant V. It means it is showing the change of pressure with respect to temperature at constant volume. Now there is a relationship between alpha, beta and gamma that you must learn, that is alpha is equal to beta gamma P. Okay, one more thing, del H upon del P at constant T is equal to V 1 minus alpha T. This relationship shows the relationship of alpha, beta and gamma with the equation of state. Now see, heat capacity. What is heat capacity? Actually, if you want to raise the temperature of any substance, okay, then heat is required. So the amount of heat that is required for raising the temperature of any substance by 1 degree is called its heat capacity. It means if you want to increase the temperature by 1 degree, then the amount of heat that is required is called the heat capacity. Okay, it is denoted by capital C. Okay, when you are using it for the solids and liquids, then you will use Cm. But when you are using it for the gases, then actually there are two types of heat capacity. One is heat capacity is when recorded at constant pressure. It means when the pressure is kept constant. In that condition, it is denoted by Cp. Okay, and it is given by del H upon del T at constant P. Similarly, the second one is heat capacity at constant volume. It means when we are recording it at constant volume. It means when we are keeping the volume of the system constant, then the heat required for raising the temperature by 1 degree is called heat capacity at constant volume. It is given by Cv and it is equal to del U upon del T at constant V. Now see the relationship between Cp and Cv. That is very much important thing. Actually, one relation I think you all know. That is Cp minus Cv is equal to Nr. Okay, but if you are taking the molar heat capacity, it means Cpm or Cvm, then Cpm minus Cvm will be equal to R. This relationship you must all know. Okay, the second one is, see here, Cp minus Cv is equal to T del P upon del T at constant V del V upon del T at constant pressure. The next one is Cp minus Cv is equal to alpha square Vt upon beta. Now we come to the internal energy. Actually, internal energy is denoted by U. It is a state function. Okay, it is the first state function that we are dealing with. State function means any function that depends upon only the initial and final state. It means it is not depending upon the path. It is depending only upon the state, initial state and final state. Okay, so this is called a state function. And actually internal energy is the total energy of the system. That is the kinetic energy plus the potential energy. U is equal to U kinetic plus U potential. For monoatomic gas, if you want to find out UMT, it means internal energy, molar internal energy at temperature T is equal to molar internal energy at temperature 0 Kelvin plus 3 by 2 RT. It means here you have taken only the translational modes, because in the case of the monoatomic case, there is only translational degree of freedom. Okay, there is only translational degree of freedom present. So you are taking only 3 by 2 RT. Now for the linear polyatomic molecules, this is given by UMT is equal to UM0 plus 5 by 2 RT. Here you are taking the translational as well as the rotational modes. Okay, so it is 5 by 2 RT. This thing you should notice. Okay, if you want detailed video, then you can see. I will give you the links. Okay, for non-linear molecules, UMT is given by UM0 plus 3RT. Here you are seeing the translational modes plus rotational modes plus vibrational modes. All three are considered here. Okay. Now for ideal gas, if you want to find out the internal energy, generally you have given the processes and you will have to find out the internal energy. Then what you have to do? You will have to use this formula. Del U is equal to integration CV dV. It means you will have to put here the value of CV and dV. Then you have to do the integration. Now if this CV is the volume dependent, it means if it is having any volume term, or you have given that it is depending upon the volume, then you will put it under the integration. If it is a constant, then you can put it outside the integration. Now see, the next thing is the enthalpy, H. This is the second state function. It is also a state function because its value depends only upon the initial state and the final state. Actually, H is given by U plus PV, or del H is given by del U plus del NG RT. You can put instead of PV and RT. Okay, and here you are taking del NG RT. Now you see here, this del NG means the number of atoms of gaseous molecules. Okay, it means number of gaseous atom. This is giving Ng. Okay, Ng is this one. It means you have to see the change in the number of product minus number of the reactant molecules, and you will have to consider only the gaseous atoms. So by using this formula, you can find out the del H for any reaction. It means if you have given the products and the reactants, you can find out the change in the number of the reactant and the product molecules, only gaseous atoms. Okay, you will have given del U, then you can find out del H. But if you have not given this thing, you have given the another thing, you have given the value of PV. Okay, then you can use this formula. Del H is equal to del U plus P2V2 minus P1V1. Okay, so means to say either you can use this formula or you can use this formula. For ideal gas, you will use the formula del H is equal to integration Cp dt. Similarly, you will have to see here, you are using Cp. It means heat capacity at constant pressure. Okay, if it is temperature dependent, then you will put it under the integration. If it is a constant value, then you can put it outside the integration and you can use this formula. This is a very important formula. Now see something about the work and heat. These two are the path functions. It means these are not a state function. These are path function. Its value depends upon the path. You know, work if you are doing by one pattern, it will have another volume. And if you are doing by another way, then it will have a different value. It means it is depending upon the path. So it is a path function. Similarly, heat is also a path function. Now, one important thing is the sign of the work and heat. If you have given expansion work means work is done by the gas. It means piston is moving upward direction, in this direction. It means the volume is increasing. Then work is negative. Similarly, if you have given the compression work, it means piston is going downward. Then work is done on the gas, the volume is decreasing and work is positive. Okay. Now similarly you can see heat, if it is absorbed then it is a positive quantity, and if it is emitted then it is a negative quantity. Now when you know about the work, heat, and internal energy. Then comes to the first law of thermodynamics, FLOT. Generally, you will see plot. That is first law of thermodynamics. That says energy is not being destroyed. Okay, energy is being changed from one form to another. It means the total internal energy of the system is equal to Q plus W. It means if you are giving heat, then either it is used to increase the internal energy or doing work. Similarly, if you are emitting the heat, then it means work is done on the system or internal energy is being expensed. Okay, so only there is a change in the form of the energy. Now see work done in the isothermal process. Isothermal means when del T is equal to 0. It means no change in the temperature. This is called isothermal process. One thing you should note. If you have given an expansion work in vacuum, it means you have given that there is expansion in vacuum or against 0 external pressure. If you have given this thing, then work will be equal to 0. This is very important thing. This you should mark. Okay. Second thing, if you have given a work done in irreversible isothermal process, it means our process is irreversible and isothermal. In that case, there will be an external pressure, constant external pressure. So work is given by W is equal to minus P external V2 minus V1. Okay. Similarly, you can put instead of V2 nRT upon P2, you know PV is equal to nRT. Okay. So instead of V, you can write nRT upon P. If you have not given the value of V, then you can put the value nRT upon P. So the formula now changed. W is equal to minus P external nRT upon P2 minus nRT upon P1. Or you can write nRT P external 1 upon P1 minus 1 upon P2. In this manner, you can use any of the formula. But if you have given the work done in the reversible isothermal process, means process is reversible and isothermal for ideal gas, then work is given by 2.303 nRT log V2 upon V1. This formula is very much important because most of your questions are asked from this formula. Okay. Now see the adiabatic process. Adiabatic process, it means if you have given a system in this manner, okay, and no heat can go outside or inside. It means there is no exchange of heat. Q is equal to 0. Its walls are actually insulated. So heat cannot go outside or inside. So Q is equal to 0 means to say Q plus W is equal to del U or del U is equal to W means to say if work is done, that it is done on the expense of internal energy because there is no heat provided. Okay. So if work is done, it means internal energy will decrease or temperature will decrease. For adiabatic process, you will use these formulas. P1 V1 to power gamma is equal to P2 V2 to power gamma. Or T1 upon T2 is equal to V2 upon V1 to power gamma minus 1. If you have to find out the work done in the adiabatic process, then it is equal to del U. So you can just find by integration CV dt. Now see the next thing, that is Joule-Thomson coefficient. Actually, what is Joule-Thomson coefficient? If you want a much more better way, descriptive way, if you don't know about it, then you can go on my app or my channel and you can watch the video. Okay. In a short manner, I am showing you. See here, what is happening when you are passing a gas from a region of high pressure to a region of low pressure through a porous plug in a adiabatic system. It means where the enthalpy is constant, then what will happen? There is a decrease in its temperature. It means it will undergo the cooling. This is called the Joule-Thomson effect. Okay, and it is shown by a coefficient, that is Joule-Thomson coefficient. So mu is equal to actually del T upon del P at constant H, means at constant enthalpy change of temperature with respect to pressure. It means when you are decreasing the pressure, the temperature is decreasing. Okay, one more formula is mu is equal to minus 1 upon Cp del H upon del P at constant T. Okay, so sometimes you will use this formula or sometimes you will use this formula. It depends upon the things that are given to you. Okay, what is given to you? One more thing, for ideal gas, mu negative is equal to 0. It means ideal gas neither show cooling nor heating on the Joule-Thomson condition. But Most of the cases shows cooling, but there are exceptions like helium and hydrogen. Actually, helium and hydrogen, these are the two exceptions that shows heating under the Joule-Thomson experiment. Okay. Now, the next thing is the efficiency of Carnot cycle. Actually, there is a Carnot cycle in which there are isothermal expansion process, then adiabatic expansion process, then there is isothermal compression process, then adiabatic compression process. Four processes are happening in the cycle in which you are getting the maximum efficiency. So the maximum efficiency that you are getting by Carnot cycle is given by T2 minus T1 upon T2, or it is equal to Q2 minus Q1 upon Q2. So these are the formula that is used, and from here generally question is asked. So this is also important. Now come to the second law of thermodynamics. Actually, basis of the Carnot cycle, the second law of thermodynamics was given. That says no heat engine can work with 100% efficiency. It means 100% efficiency means if you can 100% change heat to work, then it is called 100% efficiency. But actually, it is not possible. Heat cannot be converted to work with 100% efficiency. Can you do it? No, it cannot be done. Can you transfer a heat from a coolest thing to the hottest thing? No, it cannot happen. So this is the second law of thermodynamics that say that the natural process happens from a side of the high temperature to a side of low temperature. The heat cannot go from the low temperature to high temperature naturally. You will have to give some amount of energy. On the basis of this, a new state function was given that is called entropy. So the next state function that you see here is the entropy. Actually, what is entropy? Entropy is the amount of heat in a reversible process divided by the absolute temperature. For spontaneous process that is happening naturally is called the spontaneous process. Actually, for spontaneous process, the entropy always increases. It means the del S of system plus del S of surrounding will be greater than 0. It means it is going toward the maximity. Okay, it means it is going toward the positivity. For reversible process, the ds system plus ds surrounding is equal to 0. Okay, so now come to the criterion of the spontaneity. From here, direct questions are asked. Actually, there is a criteria for spontaneity. It means the criteria is that at constant u and v, ds should be greater than 0. Similarly, at constant v and s, du should be lesser than 0. At constant p and s, ds should be lesser than 0. At constant pressure and temperature, Tg should be lesser than 0, or at constant volume and temperature, dA should be lesser than 0. Out of which this one, and this one. These are important. Okay. So from here directly questions are asked. Now we come to the formulas for the entropy change. Okay, there are several formulas for entropy change. Now which formula you will have to use, this thing you should understand. Okay, for example, if you have given the entropy change for a solid or liquid, then you will use this formula. Del S is equal to 2.303 and Cm log T2 upon T1. Here Cm is the heat capacity of solid or liquid. Similarly, if you have given the isobaric heating process, then del S is equal to n Cpm natural log of T2 upon T1. Okay, this is for the isobaric heating. It means at constant pressure. Similarly, if you have given at isochoric heating, then you will use NCVM. Okay, means heat capacity at constant volume. Then natural log of T2 upon T1. But if you have given a general process for an ideal gas, you will have to find out the entropy change. Then you will use this formula. So if you have given nothing, you have given an ideal gas, then this formula is used. Okay, so in most of the cases, you will use this formula. Del S is equal to n CVM ln T2 upon T1 nr ln P2 upon V1. When you are converting this natural log to the log E, then you will write here 2.303. You will have to multiply by 2.303. Okay. Similarly, if you have given the isothermal process, then for isothermal process, two formulas can be used. Del S is equal to nr natural log of V2 upon V1, or del S is equal to nr natural log of P1 upon P2. These two formulas can be used. depending upon the things which are given to you. If you have given volume, then you will use first one formula, and if you have given the pressure, then you will have to use the second formula. Now see, one more important thing is the entropy of mixing. When you are mixing two or more gases, okay, the entropy will change. Okay, now the entropy of the mixture and the entropy of the previous one gases, individual gases, these are different. So you are finding out the entropy of mixing. It means the difference between them. So this is very much important. From here direct questions are asked. You will have given two or three gases and you will have to find out the entropy of mixing. So you will use this formula, del S is equal to minus R summation of xi natural log of xi, or minus r, suppose you have given three gases, then x1 natural log x1 plus x2 natural log of x2 plus x3 natural log of x3. Okay, here x1, x2, x3, these are the mole fraction. Okay, these are called the mole fraction, and this is given by, suppose you have given two gases. Okay, suppose there are two gases and their number of moles are n1 and n2. Then it is given by x1 will be given by n1 upon n1 plus n2 in this manner. Okay, so this is the thing that you have to remember. Now Gibbs free energy, this is the next state function. This is also a state function because its value depends only upon the initial and final state, and whenever you have given the state function, one thing you should remember, that their absolute value we cannot find out. If you have given internal energy or you have given enthalpy, you have given Gibbs free energy, anything, you cannot find out their absolute value. You are finding their difference in the values, initial and final state, difference between them you will have to find out. So here minus del G is representing the net work other than the expansion work at constant temperature and pressure. Means the decrease in the internal energy shows the net work done by the system other than the expansion work. Okay, and it is given by G is equal to H minus Ts. So del G will be equal to del H minus T del S. Okay, so this formula in most of the cases you use. Or if you use the differential formula, dC is equal to VdP minus SdT, from where you can find out the different relationships. For isothermal gas, if you have given isothermal process, then del G is given by nRT ln P2 upon P1 or nRT ln V1 upon P2. Okay, you can use any of this formula. If you have given pressure, then you will use first formula. If you have given the volume, then you will use the second formula. Now at constant pressure, suppose you have to find out the Gibbs free energy at constant pressure, then actually del G upon del T at constant P is equal to minus S. This is the formula. Now come to the next state function, that is work function. Actually it is the next state function. Okay, this is also a state function. It is denoted by A. Minus del A gives the maximum work that can be done by the system. It means minus del A is equal to W reversible. A is equal to U minus Ts. So del A is equal to del U minus T del S. Now see, one important equation is the Gibbs-Helmholtz equation. That is del G is equal to del H plus T d del G upon del T at constant pressure. Another form of it is del A is equal to del U plus T d del A upon del T at constant V. So by using any formula, you can find out the values of the different terms if you need. Okay. Now next important thing is the chemical potential. Actually, this is used in the case of the open system. When you have given the open system, then actually there are different types of the substance present. It means there may be different components, component number 1, component number 2, component number 3. Okay, and they will have different number of moles mixed together. Okay, so actually these thermodynamic properties that you are seeing, like Gibbs free energy, like internal energy, enthalpy, okay, these whole depends not only upon the temperature and pressure. These also depends upon the number of moles of that particular substance. It means if you have given any property in this manner, del X upon del Ni, you can find out at temperature, pressure and other number of moles. This is called the partial molar property. Okay, this is showing partial molar property. So you can find out any of the partial molar property in this manner. Okay, because it is depending upon the number of moles. So similarly, if you find out GI bar, this is called partial molar free energy. Okay, this is partial molar free energy and it is given by del G upon del I at constant temperature, pressure and number of moles of the other components. Means if you are seeing the third component, then number of moles of first, second and fourth etc. So we are keeping other moles constant, okay, and we are differentiating with respect to the one of the component. Okay, so this del G upon del Ni at constant temperature, pressure and number of moles of other constituent is called the mu I. This mu I is called the chemical potential of the ith component. Okay, so in this way you will have to find out the chemical potential. Now when you differentiate del mu I with respect to temperature, it means del mu I upon del T at P, N1, N2. This gives minus Si bar. This is called the partial molar entropy. Similarly, if you are differentiate the chemical potential with respect to pressure at the constant temperature number of moles, then it gives Vi bar. This is called the partial molar volume. So these are the important formulas about the chemical potential. Now there is the next important thing, Gibbs-Duhem equation. Actually, this is for the open system. If the temperature and pressure are kept constant, the chemical potential of the components of solutions do not vary independently with the change in composition of solution. It means if the system is open, temperature and pressure are constant and N1, N2, N3, etc. are the number of moles of different components. Suppose you are varying the composition of one of the component. Okay, then what will happen? Actually, the chemical potential of the one component is varying, increasing, then the chemical potential of other one will decrease in this manner so that summation Ni d mu I is equal to 0. It means this summation Ni d mu I should be equal to 0. Means if one of the chemical potential is increasing, the other should decrease so that the total chemical potential of the overall system will change. The change in the total chemical potential of overall system will be equal to 0. This is shared by the Gibbs-Duhem equation. Okay, so this is the whole things that you see in the thermodynamics. The next things are the phase diagrams. Okay, but in this video we are not considering the phase diagrams. If you want to see the phase diagram, then you can watch our lectures already available on the phase diagram, or if you want more detailed course, then you can visit our app. Okay, in a very reasonable price you will get the course of the thermodynamics and of the physical chemistry, or you can contact me. So meet you in the next lecture. If you want any more lecture, you can comment me. So prepare well for your exam and revise this video again so that your whole thermodynamics will be very easily rememberable in your mind. Okay, so hope you will do better in your exam. Keep on preparing. Okay, so very best of luck for your exam. Thank you.